Hello dear students, in this lesson we are going to learn another implementation of map interface, that is TreeMap. We are going to learn in detail such interfaces as SortedMap and NavigableMap. This would help us a lot in understanding of TreeMap behavior. And at the end of the lesson we'll have practice with TreeMap and I'll show you how you can use this map with keys that implements comparable interface and with keys that don't implement comparable interface. We are going to learn what a binary tree is, what red-black binary tree is, and why big O notation of TreeMap for its major operations is O of log n. Let's start. And to start with, I'd like to jump to the source code of the SortedMap interface to investigate what methods are introduced there. Here is the source code of SortedMap interface. It extends map interface as you can see here. The first method here in our list is comparator. This method should return comparator that is used in map to sort keys or null if such comparator is absent, and map uses natural ordering of keys. To be honest, this method wasn't used by me, and I think it is not very popular, because if you use some comparator to sort keys in the map, that means you have the reference to this comparator already somewhere in your program, and there is no need to get it from the map. And in case keys are sorted according to natural ordering, there is no sense to call this method because null will be returned. But now you at least know about this method and can use it someday in the future when this will be needed. The next method here is submap. I would even say that it is similar to sublist from list interface. The principle applied is the same here. We have to specify key from inclusively and key to exclusively, and we will get new sorted map in response. It is also worth to mention that majority of methods in SortedMap potentially may throw class cast exception, in case keys can't be cast to comparable interface or in case there is no comparator available in this map. Besides this exception, there are also a few more potential exceptions that are pretty straightforward. Do not pass null as method argument in case you don't want to catch null pointer exception, and do not pass from key that is greater than 2 key to not get illegal argument exception. The next method is headMap. It returns the view of the map that is less than key given. For example, if you need to retrieve all entries that are less than some specific key, you can use this method. TailMap works in opposite way. It returns the view of the map that contains entries with keys that are greater than or equal to the key that would be passed as method argument here. Also, SortedMap provides the method that allows us to access first and last key that in turn will allow us to retrieve value from map by this key. That's why we have first key method that returns the lowest key and last key method that returns the highest key. KeySet. The method similar to the one we have in our map interface but with clarifications to its implementation. The set that will be returned has iterator that returns the keys in ascending order. Values method returns collection that has iterator that returns values in ascending order of the corresponding keys. And the last method here that is also familiar to you, that is entrySet. It returns entries in ascending key order. That's all methods that are introduced in SortedMap interface. Let's move further and look at the popular interface that extends the SortedMap interface. I'm talking about NavigableMap. Here is the source code of NavigableMap interface. Let's look through the methods that are declared here and I will give my comments. The main feature of this map is that it returns the closest matches for given search targets. Main methods that are introduced in this interface are created to reach this goal. For example, here is the first method in our list, lower entry. It returns an entry that is key value mapping associated with the greatest key that is strictly less than the given key. I'm going to show you this method during the demo in a few minutes to make you understand how this method works on example. Lower key method returns not entry, but only key. It returns the greatest key that is strictly less than the given key. The next method is floor entry. It is different from low entry because it returns key value mapping associated with the greatest key that is not strictly less of the key, but is less than or equal to the given key that will be passed as method argument. Floor key returns not entry but only key according to the logic that we have just discussed. Ceiling entry returns entry associated with the least key greater than or equal to the given key. I always do analogy for myself with the real ceiling in my house to remember the logic for this method. So, this method should return the element that is right on my ceiling or above it. but not the element from the next floor. That's why it is said about least entry greater than or equal to the given key. Does it make more sense now? Hope this understanding will help you the same as it helps me. Ceiling key returns key according to the ceiling logic that we have just talked about. The next method, higher entry, return entry with the least key that is strictly greater than the given key. In this particular case, I always want to get element from the next floor that is closer than other elements to my ceiling. This is example in case we want to continue real-life analogy with the house that we started during the learning of previous method. Higher key. I believe you already understood the way how these methods are structured here. Also, NavigableMap will provide you fast access to the first entry in the map, that is the entry with the least key. To get it, just call firstEntry method. And also, access will be provided to the last element in the tree. To get it, just call lastEntry. Here you can find methods similar to those that you saw in queue and deck interfaces. We can get and remove firstEntry from the map. For that, poll firstEntry method exists. And we can get and remove lastEntry from the map by calling poll lastEntry. Taking into account the NavigableMap is SortedMap, we also can get NavigableMap in reversed order. We have to call descending map in this case. We also can get navigable key set and descending key set. By the method name, I believe it is clear that order of keys in descending key set is reversed. Here is submap method that we also saw in SortedMap, but it works with additional method parameters. In this case, developer can specify whether we want from key inclusively or no, the same as with to key. That's the level of flexibility that is added in addition to submap from SortedMap interface. We also have headMap and tailMap methods declared in this interface with the only one difference, that we can specify boolean flag to include or exclude the key from the result. And the last three methods here are equivalent to the ones that are declared in SortedMap interface. Now it is time to practice a bit, and for the sake of the demo I prepared the file with examples. I will also share it with you so that you could practice and run the code on your computer. Let me run the program and walk you through the console output here. I declare the variable of NavigableMap type and initialize it with TreeMap object. TreeMap extends AbstractMap and implements NavigableMap. It is considered as the most popular implementation of Navigable and SortedMap interfaces. For the sake of the demo, I just put integers and strings into this map like this. And here you can see different examples of me using firstEntry, lowerEntry, floorEntry, higherEntry, and ceilingEntry methods. I used 3 as a key for all methods invocations so that you could see the difference. Here you can see that even despite the order in which we put entries, when we retrieve firstEntry, we got 1. Because integer object implements comparable interface, and integer objects know how to compare themselves with the other integers. Does it make sense? Now, when I call lowerEntry, I receive 2, because the condition for this method is that entry with the greatest key that is strictly less will be returned. But when I call floorEntry for key 3, I receive entry with the key 3 because condition is different, and it allows that key would be equal to the one given as method argument. Similar story with higherEntry and ceilingEntry, but in another direction. Here I printed map and you can see that it is ordered. I can easily get map in descending order by calling descendingMap method. And here you can see in console that all entries are sorted in reverse order. Now, the thing that you should remember is that TreeMap will throw class cast exception in case you would put objects that don't implement comparable interface. But what to do in such cases? We have to pass comparator to the TreeMap constructor that is going to be used to compare keys inside. Here I created one more map where our keys will be of type product that we used for our online store creation, and our values would be of type user. But the type of the value doesn't make big difference since sorting is performed by keys. And here you can see that I created object of comparator that we implemented during one of our homeworks and pass this object in constructor here. Now I add few entries here, And when I printed to console each key from new line, you can see that all of them are sorted in order that is defined by our comparator. That's why TreeMap is often used to sort map by its keys. That's it regarding examples of how you can use TreeMap. The next thing that I'd like to talk about is performance of TreeMap and how sorting is implemented in this container. The first thing that is worth to mention is that TreeMap is not based on hash table. It is based on red-black self-balanced binary tree. That's why complexity of algorithms for main operations like get, put, remove is a big O of logarithm n. To not dive into the details and explain what a logarithm is, I will try to explain it in easy words. The performance is not linear, that means it doesn't depend on number of elements in the map in 1-to-1 proportion, but performance is scaling as we have more elements. To visualize this in your head, take a look at this slide. You can see the visualization of mapping between number of elements and time that it takes for specific operations mapped to the big O notation. You also can find big O of logarithm n on the picture. Hope this makes things clearer. How is this achieved? Because of the red-black self-balanced binary tree. Let's learn what is it. Let me start from explaining what a binary tree is. In simple words, this is a searching algorithm that consists of the nodes or leaves that stores links to nodes that are greater on the right and nodes that are less on the left. This tree has the root, and that's why we can say that all elements that are greater than the root are stored on the right, and all elements that are less than the root are stored on the left. That's why when I need to find the specific element, I don't iterate over all elements. I go only the shortest path I have to go to find the elements that I need. What potential problem you can see in binary tree? The problem is to define the root of the tree. In case we will define the root and all following elements will be greater than the root and will be placed on the right, then I will get linked list and performance of main operation will be worse than in binary tree and will be linear. What to do in this case? It might be a good idea to recalculate the root of the tree on regular basis to have the same or almost the same number of elements on the right and on the left side of the root. That's the moment when red-black tree comes into the game. Each node stores an extra bit representing color, used to ensure that the tree remains approximately balanced during insertion or deletions. That also ensures big O of logarithm n complexity for main operations with red-black tree. Tracking the color of each node requires only 1 bit of information per node because there are only 2 colors. Does it make sense? Now you know how sorting is performed in TreeMap and how it works inside. That's all what I wanted to share with you. Let's recap what we have learned today. Today we learned SortedMap interface and NavigableMap interface. Now you know methods that are declared in these interfaces. Also we had a practice with TreeMap and now you know how you can use it. We learned what a binary tree is and what a red-black binary tree is. Now you know why performance of major operations of TreeMap has logarithmic big O notation. That's it for today. Thanks a lot for your attention and see you in the next lesson.